first talk in the morning is given by Professor Xiao-Gang Wen, Xiao-Gang, and he's going to talk about the SPT order and new states of quantum mechanics. So let's welcome him.
Thank you very much for organizing this really wonderful meeting. And yesterday we already heard a lot of talk about this topological state of matter and its relation to the entanglement and etc. So today and also tomorrow, I plan to discuss the so-called SPT order. But to understand SPT order in a systematic way, we need to also have some introduction of a topological order. So today I will give some introduction of topological order. And so the study of a topological order is motivated by the study of a quantum state of matter and their phase transition. And for the long time we thought all the phase and the phase transition is given by this, is described by the symmetry breaking. But however, the discovery of quantum Hall states and the spin liquid states, and so shows that there are states of matter which are different, but they have the same symmetry. We have a different state matter with the same symmetry. So therefore, there's no way to use a different symmetry breaking to distinguish those different state matter. So that means that those different quantum Hall states or different spin liquid states must contain new kind of order, which is have nothing to do with the symmetry breaking. So this new kind of order is called topological order. And so historically, actually topological order is not discovered by study quantum Hall state. Actually, it's discovered by study high-TC superconductor. In early days, people study possible spin liquid in high-TC superconductor, and then then when you dope those spin liquid, you may get the superconducting states. So so that's actually led to the discovery of a particular kind of RVB state called the chiral spin state. The RVB state is a notion. RVB is a notion proposed by Anderson. Try to argue it's possible to have a spin liquid which do not break any symmetry. But such a notion is very vague, and so in early days people try to sharpen such a notion. And one way to sharpen this notion is proposed by Donghai, Li, and Giannopoulos. And they suggest that the RVB states correspond to bosonic nu-1/2 Laughlin states in quantum Hall states. And but their paper never published. But this idea is picked up by Kalmar and Laughlin, and so they wrote the paper and sent it to field review letter. But their first reference actually is unpublished work by Li and Giannopoulos. And later, we developed a mean field theory for this kind of a proposal. And our point is that there is a spontaneous time reversal symmetry breaking. And the one effective theory of this kind of chiral spin states is the U1 Chen-Salmon theory. But however, during this study, we realized that there's a different kind of RVB states. They all have a same time reversal symmetry breaking. This order parameter is the same. And they technically it corresponds to this so-called pi flux phase and pi over 2 flux phase and etc. You could also have pi over 3 and pi over 4. Those different flux phase. So therefore, the different flux phase actually give rise to different Chen-Salmon theory with different level and different fractional statistics. So we get this picture. When you have time reversal symmetry and parity symmetry breaking, there are still different kind of state labeled by an integer. So that's led to this notion of something beyond the symmetry breaking. So that's kind of topological order. And one way to prove this topological order actually is to study this the ground state degeneracy. But at that time, I was just switched from string theory to condensed matter. So I don't know what is ground state, but I know what is a vacuum. So the ground state degeneracy is referred as a vacuum degeneracy, which is very strange in condensed matter community. And so in this paper, we propose that we can use this different ground state degeneracy and the torus try to measure or distinguish this kind of different chiral spin states correspond different flux. So this really but the chiral spin state is a theory of a high-T superconductor. It's a special theory is because it's a falsifiable theory for high-T superconductor, which is quickly falsified. So it's not a theory for high-T superconductor, but later we realized that the same theory can be applied for quantum Hall states. So therefore, this topological order actually is really a notion of quantum Hall states. I just mentioned that the ground state degeneracy is one way to probe different kind of topological order. So we can use this ground state degeneracy as a defining property, because a concept in physics has to be defined by experiments. So this is different from mathematics. In math, to define a concept, you just need to give a definition. In physics, to define a concept, you need to design the experiment. So definition of a concept actually design the experiments. Certainly, here I just designed the numerical experiments. Basically, really to define this topological order, we really need to define some property which we call topological invariant. And such property is robust against any perturbation. So therefore, some kind of universal property. So we can use this universal property to characterize different quantum phase. So those phase, this property, which is a function for Hamiltonian, but which is robust against any perturbation. But if you add a large perturbation may drive phase transition, then this property may change. So this kind of universal property can change only after phase transition. So therefore, we can use this universal property to characterize different order. So this ground state degeneracy actually belong to this type of topological invariant. And so therefore, by having such kind of a quantum number of topological invariants, actually this became some kind of a practical definition of topological order. But however, as someone already mentioned, the ground state degeneracy do not characterize all possible topological order, because the ground state degeneracy do not carry much information. So we hope to get more topological invariants which carry more information about the topological order. So one such actual topological invariance actually is so-called robust non-abelian geometric phase. Because when the ground state have a degeneracy, then when you deform the torus or when you deform the Hamiltonian, this ground state subspace also deformed. And we'll go around the loop, and then you can define this non-abelian geometric phase. A non-abelian geometric phase actually carry much more information. So therefore, once we have a ground state degeneracy, we also have a non-abelian geometric phase, this matrix U, and then we can use this to define topological order. Actually, it's possible that this kind of non-abelian geometric phase may form a complete characterization of a topological order in any dimension. But however, the price to pay is that you probably need to consider the top space with different topology. In 2 dimensions, the space with different topology is easy to list. It's just a different genus. In 3 dimensions, to list all the possible space with different topology is a very challenging problem. So this non-abelian geometric phase can carry a lot of information. But certainly, these two property topological invariants actually, although practical, but only practical in numerical sense. They are not practical in the experimental sense. So the experimental accessible way to measure topological order actually is to measure edge states, which could be gapless edge states or could be degenerate edge states. I should also include degenerate edge state here. And actually, when you have a system with topological order, we will try to you add a few holes to the system with a boundary. Then the system with boundary either have a gapless edge extension, or it has the degenerate ground states. So so this gapless edge station and the degenerate ground states also fully characterize different topological order. But here the situation is more complicated, because when you create a boundary, there's many different ways to create a boundary. So therefore, the boundary property depends on how you make the boundary. So therefore, the correspondence is not one-to-one, so it's more complicated. But on the other hand, the boundary property indeed carry all the information about the bulk topological order. So actually, this is a form of this holographic principle. So actually, quantum Hall states, which realize this holographic principle, and this boundary bulk correspondence also is kind of holographic principle. And but the holographic principle was proposed, I think, is later. So another thing I want to mention that there's in addition to quantum Hall states, actually there are other experimental realizable topological order. The simplest one actually is a one-dimensional Fermion system. And so we know there's a search for the Majorana zero mode, but actually the search for Majorana zero mode is actually the search for this topological degeneracy, for the open chain. And so these two are really equivalent. And so therefore, if you find this Majorana zero mode on a one-dimensional, say, superconducting chain, so that would correspond to finding a one-dimensional Fermionic topological order. And that would be the example that on the end of one-dimensional chain, we don't have a gapless excitation because that's zero-dimensional. But we do have a robust degeneracy, which is so this kind of degeneracy for the chain cannot be lifted by any small perturbation. So there's a robust topological degeneracy. And so recently there's some experimental news about finding such Majorana zero mode. But I think at the moment it's still a little bit controversial, and we probably need more experiments. Okay, so let's describe this idea a little bit more. So why this non-abelian geometric phase can be used to fully characterize topological order, and what I mean by robust non-abelian geometric phase. So let's go into this notion a little bit deeper. So one way to understand this non-abelian geometric phase is to understand that for two-dimensional system on the torus can have a shape. So if you say if this the base is just a 0 and 1, then the other edge can be described by a complex number tau. So we have a periodic boundary condition. So this is a torus. So the shape of torus are labeled by a complex number tau. So therefore, this is this upper half plane. So upper half complex plane can be viewed as a shape of a torus. That's moduli space for different shape of a torus. Then I mentioned that on the torus there's a ground degeneracy. So for every choice of tau, the ground state subspace is a ground state from a subspace in this huge Hilbert space. And as we change this tau, then this subspace would start to twisting in a big Hilbert space. So therefore, the ground state's degeneracy defines a fiber bundle or vector bundle on this moduli space on our upper half plane. And so this vector bundle will have a connection. And so the first I want to say that this connection is only have U1 part. It's purely U1. So that means that we have this connection which is a matrix. And when you do this matrix value different one form, when you do this loop integration in the moduli space, so this moduli space, if you go around small loop, then this one gives us a phase. And this phase actually is just e to the I beta. If I do this alpha beta, then that's a delta alpha beta. So it's diagonal. It's only purely U1. So you may ask why this kind of when you go around a small loop, this connection only give us pure U1 phase. The reason is that the ground degeneracy is robust. It's cannot be lifted by any local perturbation. However, when you go around a small loop, this kind of a change, or it's kind of like a measurement, and this is a local measurement. And because when you deform the system, the deformation is local. And when you go around a small loop, it only takes a finite amount of time. So therefore, the propagation for the causality, the propagation of a perturbation also only finite. So therefore, this so going around a small loop corresponds to some kind of finite perturbation or local perturbation to the system. If a local perturbation can distinguish different ground states, means if this loop integral is a non-trivial unitary matrix, that means you can distinguish these different ground states. You can split degeneracy. And we say that is impossible because we already say that the ground degeneracy is robust against any local perturbation, and certainly against this kind of measurement. And so therefore, this measurement cannot distinguish different ground states. So therefore, it can only be a total phase. So all the ground states respond the same way. All the different ground states have same response. And so can only have an overall U1 phase. And there's no distinction between different ground states. And this is very important, yes?
So why is it like 3 punctures? You say it's a torus.
No, I'm not there yet.
Oh, okay, sorry.
So therefore, we only have this pure phase. Okay. And so what do you mean by non-abelian geometric phase? Because here only have U1 phase, so there's no non-abelian geometrical phase. And then it's related to actually the moduli space actually is not the upper half plane. Actually, the moduli space is the upper half plane quotient out by so-called mapping class group. And for the torus, two-dimensional torus, the mapping class group is SL2Z with some projection. Okay. And so to understand this is the following. For example, we can consider this kind of so-called Dane twist. So we can change tau to tau plus 1. So from here is tau change from tau to tau plus 1. But when tau change from tau plus 1, the tau and the tau plus 1 actually describe the same torus with the same shape. Because the tau and the tau plus 1 only differ by a different choice of coordinate on the torus. If you do this, there's a mapping from the torus back to itself. We change its coordinate, which change tau to tau plus 1. So actually these two shapes are different shape. But these two shapes actually the same shape. They only differ by a choice of coordinate. So therefore, so this is just an example. So for every mapping class group is a map which map torus back to itself onto itself. For different mapping class group elements, we can have this kind of a so-called large loop. So we deform from here to here. This loop is not contractible, but still a loop because this shape and this shape are actually the same shape. So therefore, the moduli space non-upper half plane actually is as mentioned, it's a sphere with 3 punctures, and so we can go around the 3 punctures, and so which is so this one of a loop go around the 1 punctures, and so when you go on this 1 puncture, this deformation loop is not contractible, cannot be viewed as a local perturbation. So in this case, there is no argument to say this kind of non-abelian geometric phase must be pure U1 phase. So in this case, it can be non-abelian. So therefore, what we have is that for every element of a mapping class group, we have, for example, the Dane twist. We can have this loop and a non-abelian geometric phase for this loop is some kind of a unitary matrix up to some U1 phase. And this U1 phase is path dependent, so it's not it's difficult to determine. And certainly, there's other generator for mapping class group, like a 90-degree rotation is a map from torus back to self. And also, when the torus have this kind of shape, the 60-degree rotation also map torus back to self. And so all these non-abelian geometric phases actually generate a projected rotation of this SL2Z. And this is so-called modular representation of SL2Z. And this may carry a lot of information, maybe all the information of a topological order in 2 dimensions. So so actually at the moment it's very desirable to develop a topological order based on this kind of a point of view, but so far we don't have that yet. But this it would be very nice to have this kind of topological order theory. So those kind of a general point of view. And so here I want to mention that actually this non-abelian geometric phase is closely related to the partition function of a system, or so-called topological partition function. And to understand such a connection, so let's consider space-time, but a special one. And usually when we have a space-time, we may have a most natural space-time would be the let me see, the m times s1 t. So t is time direction. So time is a loop, and this is a space. M is a space. So this is Euro space-time. But here we consider a little bit more strange space-time. Is that when we go around the time direction, we have to glue this m to m, so to form this space. But here, when we glue 2 spaces together, we don't glue them directly. We glue them after this mapping class group. So we make a transformation to map this space to itself, but this map may be non-trivial, may not be this this trivial map. So therefore, and so if you glue this space together around the loop, time loop, after a twist, we define a Ferri bundle over the circle. So here I just introduce this notation. So this is a Ferri bundle over the circle with the twist W. W belongs to this mapping class group. So we can see that this non-abelian geometric phase, which defined for every element in mapping class group, can be associated with this Ferri bundle over S1, which is a space-time defined this way. And in particular, the path integral over such a Ferri bundle over S1, we get a partition function. And this partition function happens to be equal to the trace of a non-abelian geometric phase we defined before. So this is a connection between non-abelian geometric phase and the partition function. So therefore, when we define the partition function on this special Ferri bundle, actually this Ferri bundle has a name called the mapping torus. That's a mathematician's name. If you define the partition function on the mapping torus with the trace W, then this partition function happens to be the trace of this non-abelian geometric phase. But actually, the situation is not that simple. It's a little more complicated because the partition function contains so-called non-universal part. So actually, the partition function on the space-time, the leading term is something proportional to the volume of a space-time. And that simply grounds the energy, because when you have a partition function, we know the leading term in the partition function is a grounds energy times time. And the grounds energy is proportional to the area of the space. So therefore the partition function for the imaginary time path integral, the leading term is energy density times space-time volume. So this is the leading term. And here we make a claim. This claim is not shown, and we don't know how to actually formulate claim precisely. But anyway, we make a claim. Is that this is the only term. The next term is the volume independent term. So this term do not depend on the volume. And the volume dependent term is not universal, but the volume independent term is universal. It's called a topological partition function. Okay. And there's no other term. There's no, between the volume and the constant term, there can be the length to the first order, length to the second order, and etc. Depend on the linear size of the system. And we can try to say, we can argue or wish, I shouldn't even argue, we wish or we believe religiously that such other term is not there. So just this their volume. And this notion is very much like topological entanglement entropy, where we have the area term, which is not universal, but the constant term is universal. And here is the same thing. The volume term of a partition function is not universal, but when you extrapolate back to the zero volume limit, then you get the universal topological partition function. And it is this topological partition function is a trace of this non-abelian geometric phase. And this kind of topological partition function is a subject which is very interested by the mathematicians. And because mathematicians try to classify manifold. And so how to classify manifold? They try to define a function. So the manifold with same topology, this function has same value. When the manifold have different topology, and this function have a different value. And this topological partition function happens to be such a nice function. That's when the manifold have different topology, it have a same value or different value. When the manifold have same topology, they have a same value. So we can use this function to classify different manifolds. And this is also called a topological invariant by mathematicians.
So why the topological term will not depend on coupling? Not depend on coupling constant? I can understand it will not depend on volume for some case, but why not depend on coupling constant?
Because of this, let me see. In a sense, this volume dependent term is something local. If the wave function, if the system changes locally, then you have this volume dependent term. But however, the topological term is something. This leading term somehow is representing something non-local, something global, and so then there's notion that this kind of global things, for some reason, is kind of quantized. So, but this you have a very good question. Is that in order for this global nature to be quantized and robust, universal, it's very important that the system must be gapped and have short-range correlation. So therefore, the system are nearsighted. Naively, the system cannot see anything global. They only see local information. So then you get some kind of volume term, which may depend on local coverage actually. And but somehow there are some global feature survive, and this global feature the system not supposed to see but somehow survive. This is something long range, and so that's maybe the universal part of the wave function. So basically, I couldn't explain better. It's the intuition we have here is actually the following. It's very simple. When you have a system described by product states, you can easily see that for the system described product states, the partition